Structures. My name is Sergey Grishechkin. I'm from Tel Aviv University. My co-organizer Igor Stanek is from University of Twente in Netherlands. And we have some speakers today. Our symposium, and the first one is Sergey Grishechkin, our representative from industry, from the PTC Corporation. And he will present his topic on design of lattice structures in PTC Creo.
Thank you. So it will be a little bit unusual because I need to be sitting to use the mouse. Good morning, everyone. I represent PTC. PTC is one of the 3 largest high-ed companies in the world. And our main CAD product is called Creo. So it is very sophisticated, supports like many things. And today I would like to show you what we are doing in additive manufacturing, particularly in lattice area. So I'm not a scientist. So please do not expect anything like theoretical new from me. But at the same time, I don't want to be just a marketing guy who will show you some beautiful pictures and that's it. So I would like to follow some logic and explain what we support and why we support these things. So lattices have different meanings in additive manufacturing than, for example, in mathematics or physics. If we restrict ourselves with ball beam lattices, then generally it is just some graph of beams that are connected to each other. Something like that you can see on this slide or on the next one. But I always think about lattices as some analog of crystal structure that we can create by ourselves. So obviously the topology of lattice, how knots are connected to each other, play important role. We know it from nature, when the same carbon atoms connected like in different ways result in completely different materials. So creating these lattice patterns of connections is obviously one of the basic fundamental tasks. In many cases, we expect some sort of regularity of like symmetry from lattices. It is a pretty fuzzy term, and if you want to make it mathematically rigorous, we immediately go into some deep geometry theory and discover that there are way too many symmetrical cases. And honestly, nobody would support them in software. And what is more important, we, like as a software company, actually don't have any request from industry that it is really needed. So in such a situation, first things should come first, and at the beginning, we should start with the most natural and important cases. And most natural is obviously like cubic lattice and its modifications. So let me show you how it works in Creo. I open simple part, and I would like to create a lattice. I go to the lattice. I would like to replace the solid material in this part with a lattice structure, so I'll click Replace Body with Lattice, but at the same time I would like to have existing surfaces with some thickness. So I will click Create Shell and also exclude the front surface just to get your ability to see what's happening inside. Now I go to the cell type, and here you see icons, the list of icons that corresponds to the cell topology that we support. And the simplest is cubic, but what is important to understand, it is just some sort of shell. So if I unclick everything except outer beams, it will be just cubic. But you can add any diagonal element. You can like this or this, something like that. But it's all will be inside cubic. So in this way, you can create most of the most common lattice types. And in more general way, you can just put arbitrary geometry inside this cubic and just replicate it all over the space. But I don't want to talk about it today. So this is a cubic, more general parallel piping, because you can have different dimensions and different sizes and XYZ dimensions, and also some angles. So let me make it a little bit smaller. And then I'll just click OK. And we get our lattice. So something like that. So obviously it is a periodic pattern. Unit cells here is a cube or more general parallelepiped, and you can tile the whole space with these parallelepipeds, obviously. And this actually the fundamental property that we should expect from any unit cells. They should be able to tile the whole space. And here the natural question arises. Are there any other symmetric tiles besides cubic patterns with the same property, that we can tile the whole space? It is well-known mathematical problem, and actually it was solved for the first time by this guy, Yevgraf Fedorov, in 1885. And these there exist only 5 types. They are called parallelohedrons. So this is a cubic, hexagonal prism, a rhombic dodecahedron, elongated dodecahedron, and truncated octahedron. And because of their fundamental role in the theory, we support all of them in Creo. So if I will go back to Creo and click Edit Definition, then all these 5 types are here. So it's like a rhombic dodecahedron, for example, here. Maybe you can think that some of these shapes are too complex, too theoretical. But as we already heard today, there is nothing more practical than good theory. And this is the case in the also. So for example, this particular pattern, rhombic dodecahedron, it was direct push from industry to support this kind of thing. So a big European company, which is called Wright, that is specialized in medical implants, approach us, and they need exactly this topology, because it was the only topology that was approved by European regulator for these purposes. The next topology, it is elongated dodecahedron. It's also quite interesting. It is closely connected to the next 2 shapes that are actually axetic materials. 2 axetic materials. Let me explain a little bit about axetic. Pretty interesting thing. So axetic is the same as materials with negative Poisson ratio. So if you stretch them in one direction, they will extend in the perpendicular direction as well, contrary to conventional materials. Such materials have various practical applications, and they don't exist in nature, almost don't exist in nature. But it's pretty easy to make them using lattice structures. In 2D, the simplest and most popular structure is the following. You can see it on YouTube video. So you just take a hexagonal cells and flip some of the edges inside and get the axetic lattice. 3D analog of this thing exists as well. You can see it on the right. And axetic properties depends on this re-entry angle theta. Note that we do have only one re-entry angle for both 2D and 3D. And it looks a little bit suspicious. Just from abstract mathematical logic, if you have 1 degree of freedom in 2D, then probably you should expect more than 1 in 3D. And otherwise, it's not a proper mathematical generalization in some sense. And when I thought about it for the first time, my idea was, okay, in 2D we have only 2 possible tiling of the space, of the plane. It is a rectangular pattern and this hexagonal pattern. And if you flip edges inside in one of these patterns, we get axetic materials. So maybe we can do the similar things in 3D as well. We do have these 5 patterns. Let's try. And it immediately turns out that yes, this is the case. The 5th pattern, the elongated dodecahedron, can be flipped inside, and in this way we get axiatic structure. So it's very well known from geometry, but probably was never used in the context of additive manufacturing. If you compare both of them side by side, it's different patterns. So this new axiatic structure, you see it's shifted in half. Each layer is shifted in half. And also the connection of beams are different. We can create both of them. It's, yes, it do have two angles, two re-entry angles. So let me demonstrate how it works. So I go to the edit definition again. This is our axiatic unit cell. So I can enter, for example, 5 degrees here. It's not symmetric anymore. Click OK. And get this axiatic structure lattice. So this was the reason why we supported both two options for axiatic. And yes, they are both axiatic. We checked it using simulation. So they're both axiatic. That's like here. Now the last pattern in this gallery. So back to Creo. Edit definition. Our last pattern is stochastic lattices, this one. Stochastic lattices are very important. So usually they're based on Voronoi decomposition of space. And cells in this case are some convex polyhedron of random size and random shape. Stochastic lattices they do have many unique features. First of all, they are isotropic by their stochastic nature. Second, they can follow the shape of the object, which is not possible for regular lattices. Follow the shape, including the edges. So let me demonstrate how it works. I would like to create just surface lattice here. So on bounding surface only. Click OK. So this is a surface-only lattice. You see how nicely it follows the edges. So Voronoi do have dual structure, mathematical dual structure, which is called Delaunay triangulation. So we support both of them. You can see Delaunay and Voronoi here. If you compare them side by side, the difference, this is a Voronoi. So it's like foam, very soft. And this is a Delaunay. It's triangulation, all triangles, all tetrahedrons. So it's like opposite side of physical properties, very, very strong. Stochastic lattices are so important also because of the applications. So one of the most important applications are biomedical, because the similarity of stochastic lattices with human bone structure. So typical example is a hip joint replacement surgery. The implant itself contains several parts, but the most critical is the acetabular cup. It goes inside the human pelvis. And the outer part of this cup should be porous. It is extremely important because pelvic bone should grow into these pores. So eventually, after the surgery, it becomes just inseparable unit, just one unit. And stochastic lattices are de facto standard here because for such porous materials because they highly resemble the real human bone structure. So this is a basic lattice patterns that we support in Creo, like ball beam patterns, but this is just basic. State-of-the-art capabilities are down the road. So probably the most important generalization is the variability based on, for example, simulation result, or in general, like space variability. So you have your simulation results. This is the one with the stress, and we would like to replace the solid material with some lattice with a density that would correspond to these stresses. So you have actually two options. You can keep the regular lattice, and in this case you need to vary the beam thickness. This is the picture in the middle. Or you can work with stochastic lattices. In this case the beam thickness would be constant, but you vary the cell sizes. Both of them serve the same goal. So Creo supports the whole workflow. You can work directly with Creo or ANSYS simulation data, or the most universal way, just specify the desirable density, the desirable volume fraction in a file. Just put XYZ volume fraction, XYZ volume fraction in a file, and Creo will create lattice structure with exactly this volume density, smoothing the data between specified points. A similar but different problem. In many applications, it is important to have specified pore sizes. So you want not the density distribution, but pore size distributions. The primary application, again, biomedical, where exists pretty strict specification about pore sizes. But let me give one more example, filtration. It is probably the first thing that comes into our mind when we hear like pores. All of us have some sort of filters like for air, oil, water in our homes and cars. Usually it is just plain filters, just some sheet of filtration material that is bent in some zigzag pattern or something like that. But what about if you want to make the so-called deep filter, volumetric filter? So simple example. Go back to Creo. So I have this cylinder, it's 400 inches long, and I will create a stochastic lattice. We specify pore size. So I specify target pore size, let it be 6, and also let the diameter of the beams would be 2, so we can compare. Click OK. This is the result. Now imagine that we put such a thing inside a pipe. So fluid goes from one end to another end. The question, is it a good filter design or bad? The answer, it is bad. Why? Because what happens, like all pores are absolutely the same size. So the entry layer of this filter will be contaminated almost immediately. And the filter will be clogged. And the whole remaining volume of the filter will be almost clean. So the good design, how to create the good design, there's obviously some science behind that, but very roughly, you should have big pores at the entrance, big pores at the entrance, and then become smaller and smaller and smaller. So what happens if a contaminated particle is large? It will be captured at the very entry level. And if they are small, they will go inside and captured inside the filter. So what we can do in Creo? In Creo, we can follow any custom pore size distribution. Just specify it again in a file and we create whatever you want. So let me demonstrate how it works with this cylinder. I go back to the edit definition of this lattice. Go to the density tab, simulation, and choose a file. I can actually create, I have two patterns, like linear increasing from 2 to 10 of the pore sizes, or like sinus. I don't know what is better. Let's do sinus maybe. So I click OK. OK. Few seconds. And this is the result. So you see that the pore sizes are variable. So let me just show you a little bit more pictures, beautiful pictures, what we can do this way. Just any distribution you want. And now the last topic that I would like to cover today. It is about a lattice merge. So I described some patterns, like standard patterns. But what if you would like to have the 2 different or 3 different lattices within the same body? So, simple example, as in this picture. We have cube, and we have some surface that divides this cube into 2 areas. One lattice inside, one lattice outside of this surface. And we would like to merge them together. How we can do it? The simplest way is just blend everything into this wall, but it would be wall. In many applications, it doesn't work. What we want to do, we would like connect blue beams with green beams directly in some meaningful way. Is it possible or not? And our goal is to do it in general case, in 3D, for any lattice types, any orientation, any sizes, just anything, and any dividing surface between them. It looks like a little bit problems that cannot be resolved, but we did it. So this is the result for this particular lattice. You see, we merged them very nicely. So before and after. And this is actually, it's not a 2D picture, it's a 3D picture. Let me show you. So the same thing, you see, it's like volumetric thing. How we did it? We introduced a new feature which is called lattice merge. So, example, we have We have four lattices here. Oops.
May I ask you which is the dimension of the cell you are printing? Which is the smallest possible?
The most less possible about 50 microns, I think.
Okay.
Something like that.
So the whole cell has a size of 50 microns?
Yes. So it depends. It's not about geometry. Geometry, we can create everything. It's about hardware. So I'm not responsible for the hardware. But right now, it's like about 50 microns. So, so about this notch. So we have four lattices here. You see, they're even overlapping. And we would like to like connect them together. How we can do it? I go to engineering, lattice merge, and add everything here. So you have four lattices in this list. Note that the order is important, because the order in this list is actually described the priority of the lattices. What would happen in the intersection arity? So this purple lattice in the center has the highest priority, and the dark green lattice has the lowest priority. And what you need to do, just click OK, and you will get the result. I will show the result. It is here. So we merge everything together. Every beam goes to the every beam, and again, it is 3D lattice structure. It's not 2D. So I am finishing my conclusions. I think that lattices is the core functionality, how we can create metamaterials with additive manufacturing techniques. So there are a lot of different and difficult problems in this area, even basic or theoretical, like this merge. And in CAD, we cannot support everything. But we are trying to be at the front line and support, our goal is support anything that comes from industry, which is really important, that comes from industry or research. So from this point of view, we are very open to collaboration with academia, just to let you know. So thank you.